Hello, my name is Kaoutar El Maghraoui, and I'm a principal research staff member with IBM Research. I'm affiliated with the IBM Research AI Hardware Center, leading our testbed infrastructure efforts and working closely with our partners. In this talk, I will give an overview of our work around AI hardware accelerators and the composable infrastructure. So let's start with the AI hardware accelerators. AI, and especially deep learning, has achieved incredible performances in numerous fields, including computer vision, speech recognition, NLP, or natural language processing, etc. However, with this huge success also comes increased complexity. The first thing we notice is that deep learning models are getting larger and deeper with millions or even billions of parameters. In fact, the number of parameters of deep learning models is increasing on the order of 10x year on year. Second is the increased size and complexity of deep learning models translate into high computational demands. In fact, compute requirements for large AI training jobs have been doubling every 3.5 months. Additionally, most of these models are too expensive to computationally run on devices like cell phones, embedded devices, or edge devices. And the third trend that we notice here is that this increase in computational needs also translates in increased carbon footprints and high costs. And as the future of AI is moving into the edge and AI becomes increasingly important at the edge, we need to consider more seriously a shift from state-of-the-art model accuracy to state-of-the-art model efficiency. Learning at the edge will play a key role in the future. And edge intelligence comes with various challenges, such as resource-constrained devices, CPU, memory, power, etc., the difficulty of deploying models on a fleet of devices, the unstable network connectivity, which is often not stable and not guaranteed, and the fact that data often cannot leave the edge due to privacy and security reasons, such as in the case of healthcare applications. So approximate computing techniques are becoming increasingly important, especially for inference, to allow more operations per second and to reduce the memory access pressure and also provide better utilization of the cache and deliver higher throughput and lower latency. So what's happening today with regards to AI hardware trends? It is still so broadly inefficient the way we train deep neural networks with existing hardware with GPU architectures. And this gave rise to the need for specialized AI hardware accelerators purpose-built to deploy deep learning applications efficiently, especially in real-time systems and edge devices, where there is need to accelerate DL compute to achieve low latency, less than 20 milliseconds, and also, or even ultra low latency between 1 and 10 milliseconds. And it is pretty clear that AI is the next big thing that is scaling up and driving the semiconductor industry. If we see the trends here, it is clear that specialized AI ASICs are on the rise, and there is no one size fits all. Feature requirements are different also in different use cases and hence different choices of AI chips architectures. The optimal compute architecture will vary by application use cases and hardware deployment scenarios, from edge in tiny ML applications all the way to the intermediate edge, all the way to the data center. So looking at accelerating deep learning requires hardware software innovations that are needed across the stack for purpose-built AI compute infrastructure. And this requires innovations from materials to architectures to algorithms and all the way to software. To address these challenges, in February 7th of 2019, IBM launches a research collaboration center to drive next generation AI hardware. IBM made a commitment to invest $2 billion and New York State committed $300 million over the next 5 years. And this generated a lot of interest in the technical community. Existing members include materials companies, semiconductor equipment companies, major design automation companies, and also semiconductor chip design companies. We founded the center to address the compute challenges, and we believe to address this opportunity, we require a full stack approach. We cannot solve these issues by focusing on just a single piece of the stack. It is really important to focus on the entire stack. So we have 4 technical thrust areas here. The cores and architecture thrust is about how do we reinvent compute for deep learning and AI, focusing mainly but not exclusively on digital compute, and taking strong advantage from the use of reduced precision to increase compute efficiency. Moving to the right here, when precision is reduced enough, analog compute starts to become feasible. Analog compute is challenging if you need to do 32 bits MAC operation, multiply, accumulate operations. Analog compute work better if your precision requirements are, say, in the 2 bits or 4 bits domain. And we're taking an interesting approach here of combining fundamental materials innovations with our architectural algorithmic innovations to get to even more compute efficiency with analog compute. Moving to heterogeneous integration, if you scale the compute efficiency very high but do not maintain system balance, like scaling bandwidth, connectivity, and memory capacity, you end up with a lot of unused silicon. So to maintain this overall balance, the focus here on heterogeneous integration is very important. And then finally, the end user testbed trust brings in the end users and the software ecosystem. The center is hardware heavy, but it is important to show these innovations in the context of key workloads and also to study emerging workloads from software perspective to see how they will inform future design of our hardware. So this here shows the key ingredients for efficient AI systems design. And this includes hardware, algorithms, and software. On the hardware front, compute platforms that are specialized to execute AI workloads efficiently. On the algorithms, here we focus on leveraging resiliency of the AI workloads, leveraging approximate computing. And on the software stack, there is a lot of work, in terms of compiler and ease of programmability that is needed to also glue these things together. This slide here shows, a lot of the papers that our team has published in the domain of hardware accelerators, approximate computing, and also custom compilers. What we show here is IBM Research roadmap for what's beyond the GPU. What we have plotted in this graph, the gray dots, is some existing and projected performance metrics of mostly GPU hardware that exists in the market today or has been announced by major players. And we notice that there has been a steady progress of a rate of 2.5x per year over the last few years. So the question here is, what technology do we need to develop to be able to continue this rate of progress and go beyond the GPU? So how do we put the next data point on this graph? And you see here the blue dots. So the first step is to build accelerators that exploit the fact that machine learning models are highly tolerant to reduced precision computation. And the next advances shown here with the yellow dots will come from exploiting analog or in-memory compute technologies, which could potentially offer another 100x in energy efficiency. So we're on track so far, beating these expectations so far. And how we're doing this with reduced precision requirements over time, with new digital cores, and bring in also the analog cores to reduce or to replace or supplement digital to get to a whole new level of capabilities. IBM Research has been leading in reduced precision scaling while maintaining ISO accuracy, meaning we get the same model accuracy as with the full floating points. 5 years ago, from 2015 or about 6 years ago now, we proposed the world's first reduced precision DNN training and started this precision scaling journey. Precision scaling has been very effective for hardware performance improvements in these years. In every 3 years, arithmetic precision has been scaled by 2x, which improved 4 to 6x hardware performance without losing network accuracy. And in 2018 and 2019, NeurIPS, we had successfully shown the world's first 8-bit training and continue to lead in precision scaling. And inference, we also firstly demonstrated high accuracy result for 2 bits and 4 bits. More recently, we have shown the world's first 4-bit training in NeurIPS in 2020. And the ISSCC 2021 conference, it was also a highlighted paper, IBM Research Test Chip based on 8 training and 4-bit inference was showcased. As I mentioned before, the next step in the evolution for specialized hardware for AI is really rooted in addressing the performance efficiency loss from data movement between computational units and memory. And non-volatile memory or NVM technology enables in-memory computing, which eliminates this Van Neumann bottleneck and allows performant computations directly in memory. This is accomplished by mapping the DNN to analog hardware and storing the neural network's weights as a property of the NVM material itself. And this eliminates data movement altogether. This approach can offer unparalleled speed up and energy efficiency for AI workloads. Here we show the key advantages for analog AI inference, which is, first improved energy efficiency. And this comes from, if you look at these profiles, on this picture on the top right, you see that most of the operations for neural networks across multiple domains like speech, language, and vision, they're dominated by MAC operations. And this is what analog in-memory computing addresses firsthand. So this significantly higher power efficiency for an in-memory map is key to improving the energy efficiency. The other advantage is the zero standby power. And this takes advantage of the NVM technology and also allows low startup time, no need, to fetch the weights from memory, and also very low latency, which takes advantage of the pipeline weight stationary architecture. And we're seeing latencies less than 1 millisecond for most models and workloads. And also this is very advantageous for mini batch streaming workloads where you don't need to fetch weights from DRAM and provides additional advantages against digital approaches. We're also building real analog AI inference hardware where we have showcased first of a kind industrial demonstrations of neural network inference using analog AI chips. For the first time, the IBM Research Hardware Center announced at VLSI 2021 last year a 14 nanometer fully on hardware deep learning inference technology using two types of analog AI compute chips based on phase change memory. So next, I will cover our composable infrastructure and the need for having such an infrastructure to do hardware-software co-design. As I've shown, we're building next generation AI accelerators, and it is really important to have a flexible environment that allows studying how these new AI cores or new AI accelerators work with other system level components from a workload-centric point of view. The composable system design provides flexibility to serve a variety of workloads. So you can kind of cookie cut various system topologies depending on the needs of the workload. So this system offers this dynamic co-design platform that allows experiments and measurements in a controlled environment. And this speeds up system design and software evolution. It also decouples the life cycles of components. Why this is important for the AI Hardware Center? So this allows us to experiment with various system level topologies and configurations, also understand where the bottlenecks are in the system in order to design around them, also enabled by high performance interconnect. So at the core of this, there is a PCIe interconnect switch. It's a high-speed PCIe interconnect. And then a pool of system level components can be attached dynamically to this PCIe fabric. So, and then you can draw enough resources from each component pool, like FPGAs or NVMe drives or GPUs or networking cards and so on. And you can easily plug and experiment different PCIe compatible devices. Whereas in traditional servers, we have fixed ratios of compute versus memory versus IO versus network and so on. And often these resources can be underutilized. It also will depend on the different variety of workload that you're serving. And you cannot change this topology, it's very fixed. So this shows our current implementation or configuration. This is a prototype system. Our implementation is based on the Falcon 4016 implementation. We've worked with our partner H3 platforms to design the system. Each composable system or each Falcon switch here is connected to a separate micro server. It could be any other server also. And these servers both have 40 core x86 CPUs and 8 locally connected GPUs. And the composable system adds flexibility to the system by allowing multiple configurations of resources. So I will just show some use cases of how you've used this system. So we evaluate also, in this study, the performance and sensitivity of representative AI and HPC benchmarks to see the impact of resource disaggregation. So we used here representative deep learning benchmarks to cover various ranges of model size, computation to communication ratio, pre-processing steps, etc. Like, for example, MobileNet V2, ResNet 50, BERT, and BERT large. And on the HPC side, we took two key HPC workloads, the high-performance LIMPAC, which solves a randomly generated system of dense linear equations, and in the HPCG, which uses the Krylov subspace method along with the preconditioner for solving a linear system. We've also, looked at the impacts of the composable peer-to-peer bandwidth with respect to storage or the number of NVMe SSD drives. So what happens here is the SSD write the requested data to a buffer in the memory of a V100 GPU that's connected to the composable fabric and to another. So we have two scenarios here. The orange line here shows that the GPU is in the host server, native to the host, and then the blue line shows the GPU is in the composable fabric. And what this experiment shows is that this fabric, through its network of tightly coupled PCIe switches, it allows an efficient peer-to-peer communication between the devices at low latencies and near peak bandwidth lengths. So it shows the advantage of using such an infrastructure. And here what we share is the sensitivity to storage and GPU disaggregation of various benchmarks that we have evaluated. So the DL benchmarks were not affected by storage disaggregation. However, we see a wide spectrum when analyzing the sensitivity of the applications to GPU disaggregation. What we mean here, whether the GPUs are local to the host, to the server, or attached to it through the PCIe switch. We notice here is that, it depends on how much communication is happening through the PCIe switch. For example, for BERT large, which is a large deep learning model, there is much more sensitivity to this disaggregation observed opposed to smaller models like MobileNet V2 and YOLO. So the key takeaways here is that the composable system extends the configuration options and also the virtualization of the system. So you can stand up full stack dynamically. You can also add and remove resources dynamically, and it allows you to improve the resource utilization with this flexibility. And also it decouples the life cycles of the devices. And we've also done characterization of various deep learning benchmarks, like I've shown in the previous slides. Our goal here is to use this composable infrastructure to study the new AI hardware accelerators that we are building in the context of an end-to-end deep learning or a bench. So to sum up, I've covered here our end-to-end roadmap for AI hardware to provide 2.5x performance improvements per year via reduced precision techniques, analog in-memory compute, enhanced bandwidth and memory near compute. And we've also covered our composable infrastructure for hardware software co-design and research and development. Thank you, and happy to take your questions.